Welcome, everyone, and thank you for joining us today. I'm excited to introduce our presentation on solids handling in wastewater treatment. The title of our session is exactly that, Solids Handling in Wastewater Treatment, and we'll be exploring the key processes involved in managing solids effectively. Over the next few slides, we'll cover how solids are separated from water, stabilized, and prepared for safe disposal or reuse. We'll look at the four critical functions: thickening, digestion, dewatering, and disposal or reuse that make this possible. So let's dive in and learn how this essential part of wastewater treatment keeps our environment safe and healthy. Understanding biological digestion is key to managing wastewater sludge effectively. The digestion process is essentially about breaking down sludge into simpler components, and this is primarily achieved through microorganisms. The sludge we deal with can be quite variable. For example, sludge from secondary clarifiers of extended aeration-activated sludge is already partially stabilized, meaning it's less problematic. In contrast, sludge from primary clarifiers is often unstable, odorous, and full of pathogenic bacteria, which makes it more challenging to handle. Biological digestion is the most common method used to stabilize sludge. During this process, microorganisms break down the organic material, converting a part of the sludge into gases like carbon dioxide, methane, and water vapor. This not only reduces the volume of sludge, but also makes it safer for disposal. Now, why does stabilization matter so much? Well, thoroughly stabilized solids prevent serious issues like foul odors, exposure to dangerous pathogens, and attraction of vectors such as mice, dogs, and birds. The main goal here is to reduce the volatile solids content, which is a measure of organic material that can decompose and produce odors or other problems. During digestion, this reduction is what stabilizes the sludge. And it's worth noting that digestion can occur under different conditions, either aerobic, with oxygen, or anaerobic, without oxygen, depending on what's most suitable for the treatment process. So, in summary, biological digestion is a vital step in ensuring that the sludge is stabilized, less odorous, and safer to handle, which ultimately supports the overall health and efficiency of wastewater treatment. Today, I want to talk about anaerobic sludge digestion and its key benefits. First, odor reduction is a major advantage. This process transforms wastewater solids into a substance that is relatively odor-free, making disposal much easier and less problematic for the environment and surrounding communities. Next, pathogen control is crucial. When operated correctly, anaerobic digestion significantly reduces harmful pathogens, ensuring that the end product is safer for handling and disposal. Then there's volume reduction. This process can decrease the volatile content of sludge by 30 to 60%, which means we manage much less material overall, saving space and resources. Additionally, anaerobic digestion produces valuable energy in the form of methane gas. This renewable energy can be used to heat the digesters themselves or even generate electricity, making the process more sustainable and cost-effective. Overall, anaerobic digestion is one of the most efficient and economical methods for stabilizing wastewater sludge, turning waste into a useful resource while producing renewable energy. Let's take a closer look at how anaerobic digestion actually works. It relies on two main groups of bacteria that work together in the same environment. Understanding this balance is really key to making sure the digester operates successfully. First, we have the acid formers. These are saprophytic organisms, and their job is to break down complex organic matter into simpler organic acids. Think of them as the first step in digesting waste, converting big molecules into smaller, more manageable acids. Next, we have the methane fermenters. These bacteria use the acids produced by the acid formers to create methane gas and carbon dioxide. They essentially turn the acids into biogas, which can be used as energy. Now, here's the critical part, the balance between these two groups. The key to effective anaerobic digestion is making sure the rate of acid formation matches the rate of methane fermentation. If acids build up faster than the methane bacteria can convert them, the pH will start to drop. This is important because methane fermenters only thrive within a narrow pH range, roughly between 6.6 and 7.6. Since methane fermenters are less abundant in raw wastewater, maintaining the proper pH is crucial. If the pH falls outside this optimal range, the bacteria struggle to reproduce and do their job effectively. So, keeping that pH steady is essential for the entire process to work smoothly and efficiently. Let's take a closer look at the temperature ranges for anaerobic digestion, starting with the psychrophilic range, which is between 10 and 20 degrees Celsius. In this range, cold-loving bacteria dominate. However, digestion here is quite slow and not very efficient. You'll typically see this in systems like Imhoff tanks, septic tanks, unheated unmixed digesters, and the anaerobic parts of lagoons. The main byproducts are carbon dioxide, hydrogen sulfide, and water. Interestingly, only a small amount of methane fermentation occurs in this temperature range. Moving on to the mesophilic range, which is between 20 and 45 degrees Celsius. This is where medium temperature-loving bacteria thrive. It's also the most common range used in wastewater treatment plants because it strikes a good balance, producing a high level of methane with a relatively short digestion period, usually around 25 to 30 days. The optimal temperature here is about 35 degrees Celsius or 95 Fahrenheit. Because of that, digesters in this range are typically heated, often by burning the methane they produce, to maintain that ideal temperature. Now, the thermophilic range, which is from 49 to 57 degrees Celsius, hosts hot-loving bacteria. These organisms prefer hotter conditions, but operating in this range is more challenging. Maintaining such high temperatures can be tricky, and the organisms are quite sensitive to temperature fluctuations. Plus, there have been reports of poor liquid and solid separation at these temperatures. Because of these issues, few digesters are operated in the thermophilic range. And here's an important rule to remember. Never change the temperature more than 1 degree Fahrenheit per day. This slow adjustment allows the microorganisms to acclimate gradually. Simply raising the temperature suddenly won't lead to a successful operation. It's all about giving the organisms time to adapt to the new conditions and ensuring your digestion process remains stable. Let's take a closer look at the components of an anaerobic digester. Typically, these systems are designed with two main stages, a primary and a secondary, and they operate in the mesophilic temperature range, which is around 35 to 40 degrees Celsius. The first stage is where most of the gas production happens, up to 90%. This stage is heated and mechanically mixed to keep everything evenly digesting. The second stage mainly serves for storage and allows for solids and liquids to separate, making the overall process more efficient. Moving on to pipelines and valves, you'll notice that cast iron or steel pipes are commonly used because they can handle high pumping pressures and resist severe corrosion over time. For controlling flows, especially in sludge and scum lines, plug valves are often employed. They're effective at preventing debris from clogging the system. Now let's discuss the digester tank itself. Most modern digesters are cylindrical, typically around 20 feet deep, with sloped floors. This design helps when it's time to withdraw sludge because it allows sand, grit, and heavier solids to settle and be removed easily, keeping the tank clean and functioning optimally. Regarding the mixing system, mechanical mixers are quite common. They often utilize propellers and draft tubes to keep the contents well mixed. Alternatively, some systems use mixers that work by compressing and bubbling methane gas into the sludge, which enhances mixing and digestion efficiency. Finally, the heating system is crucial for maintaining optimal conditions inside the digester. Usually, a boiler is used, which can be fired by digester gas, natural gas, or propane. The goal is to keep the boiler water between 60 and 82 degrees Celsius, often using heat exchangers either inside or outside the digester to ensure consistent and efficient heating. All these components work together seamlessly to ensure the anaerobic digestion process is efficient, stable, and productive, forming a vital part of our overall waste management and renewable energy strategies. Let's take a closer look at the gas system, which is a crucial part of the digestion process. When we talk about the amount of gas produced, we're looking at two main measurements. First, the cubic feet of gas generated per pound of volatile matter added during mesophilic digestion. Second, the cubic feet of gas produced per pound of volatile matter actually destroyed. These metrics help us understand the efficiency of the process. Typically, the gas produced is composed mostly of methane and carbon dioxide. About 65 to 70% of this gas is methane, which is the primary component responsible for energy content, while roughly 30 to 35% is carbon dioxide. It's important to note that mesophilic digestion generates a significant amount of gas, and this gas has a heat value of around 500 to 600 BTUs per cubic foot. To put that in perspective, natural gas ranges from 900 to 1200 BTUs per cubic foot, so our biogas is a bit less energy dense. Now, this gas isn't just produced for the sake of it. It has several important uses. We can harness it for heating the digester to maintain optimal conditions, or use it to drive engines or generators, producing electricity. It can also be used to heat plant buildings, which helps reduce other energy costs. And of course, any excess gas needs to be safely managed. That's where waste gas burners come in. They burn off the excess gas to prevent buildup and ensure safety. The entire gas system is designed to safely remove and utilize this gas. It includes key components like the gas dome, pressure and vacuum relief valves, flame arresters, thermal valves, sediment traps, drip traps, gas meters, manometers, pressure regulators, and the waste gas burner. Each part plays a role in controlling, measuring, and safely burning the gas, making the whole process efficient and safe. Connecting this to the bigger picture, managing biogas effectively not only helps us produce renewable energy, but also ensures safety and environmental protection. It's a vital component of sustainable waste treatment and energy recovery systems. Let's talk about critical safety aspects related to floating covers on digesters. Many digesters, especially the secondary ones, are equipped with floating covers. These covers serve an important purpose. They provide a flexible space for storing digester gas. A properly designed floating cover not only helps in gas storage, but also plays a role in maintaining the proper mixing of the scum blanket with the digesting sludge. This prevents the blanket from becoming excessive, which is crucial for efficient digestion. Now, here's a very important safety point. Extreme caution is needed because if the sludge level drops too low, the seal of the cover can be broken. When that happens, a dangerous mixture of methane and oxygen could form, and this mixture is highly explosive. There have been incidents where operators, perhaps inadvertently, withdrew too much sludge during maintenance, leading to such explosions. So, always be aware of the sludge level and handle sludge removal carefully. Another key aspect is that floating covers are designed to move up and down as the amount of gas and sludge changes inside the digester. This movement is normal, and the interior of the digester is sealed from the atmosphere by a sludge seal located between the cover and the wall. Finally, I want to emphasize that extreme caution must be exercised whenever an anaerobic digester is emptied or dewatered, whether for maintenance or cleaning. This is a critical safety step to prevent any risk of explosion. Always follow safety protocols carefully when working with these systems. Let's talk about operating anaerobic digesters effectively. The key to successful operation is maintaining a balance between acid formation and methane fermentation. Achieving this balance requires careful control of several critical parameters. First, maintaining the right temperature is essential. We want to keep it around 95 degrees Fahrenheit or 35 degrees Celsius. This temperature is ideal for bacterial activity, ensuring optimal methane production. Next, proper mixing is crucial. Mixing promotes contact between the microorganisms and the food substrate, which helps the digestion process. It also ensures even heating throughout the digester, preventing hot spots or cold zones that could disrupt microbial activity. Controlling feed rates is another important aspect. We need to feed and withdraw sludge at proper rates, making sure not to withdraw more than 5% of the digester's content in a 24-hour period. Over-withdrawing can disturb the process and reduce efficiency. Balancing the types of sludge fed into the digester is also vital. Raw sludge from a primary clarifier typically contains about 4 to 5% total solids, with 70 to 90% of that being volatile matter. Waste-activated sludge, on the other hand, can range from 0.2 to 6% total solids, with 65 to 75% volatile solids. Raw sludge tends to digest quickly, while waste-activated sludge digests more slowly and less completely. It's best to feed sludge several times a day rather than all at once. Spreading out feeding helps prevent large temperature drops and keeps the process stable. And whenever possible, we should pump in as thick a sludge as possible because space inside the digester is limited. By paying close attention to these parameters and maintaining control, we can operate anaerobic digesters efficiently and sustainably, supporting the overall treatment process. Let's talk about monitoring digester performance, which is essential for maintaining efficient and stable operation. First, temperature is a critical factor. You want to keep it between 95 and 98 degrees Fahrenheit. Usually, you'll find a thermometer in the sludge recirculation line to help monitor this. Remember, never increase or decrease the temperature by more than 1 degree Fahrenheit per day to avoid stressing the system. Next, the VA to ALK ratio. This ratio should be less than 0.1 to 1, meaning there's 10 times more alkalinity than volatile acids. If this ratio changes, that's actually the first sign that something might be off with the digester. It's a key early warning indicator. When it comes to gas content, good digester gas typically contains about 30 to 35% carbon dioxide and 65 to 70% methane. If the CO2 level exceeds 42%, it indicates the digester is in poor condition. And if it goes above 45%, the gas may not burn properly, which impacts energy recovery. The pH level is also important. A pH between 7 and 7.6 generally indicates good operation. However, keep in mind that while pH is useful for recording, it's not the best for process control because the VA-ALK ratio tends to show changes earlier. Now let's discuss solids content. It's important to determine the total solids for feed sludge, recirculating sludge, withdrawn sludge, and supernatant. Typically, the total solids in the digester should be around 3 to 6%. Finally, volatile solids reduction is a very effective indicator of how well the digester is performing. Reductions of 50 to 60% are common and point to effective stabilization of the sludge. And here's a critical point. Monitoring the VA-ALK ratio weekly is absolutely essential because it gives the earliest warning signs of potential problems in the digester. Keeping a close eye on this ratio helps us catch issues early and keep everything running smoothly. Let's talk about troubleshooting anaerobic digester problems. Careful process control and understanding the fundamentals are key to preventing most issues. However, problems can still occur, and it's important to address them quickly to keep things running smoothly. One common issue is digester souring, which is indicated by a VA to ALK ratio greater than 0.1 to 1 and a pH between 7 and 7.2. This usually happens due to excessive feeding of raw sludge, too high a sludge withdrawal rate, or shock loads. To fix this, we can recirculate secondary digester sludge back into the primary to boost alkalinity and seed beneficial microorganisms. Another problem is the digester stuck, which shows up when the VA to ALK ratio exceeds 0.5 to 1 and the pH drops below 7 and keeps falling. This often results from not correcting a souring condition early. The solution here is adding alkalinity, lime, soda ash, or sodium bicarbonate to neutralize excess organic acids and help restore balance. Foaming is also a common issue, especially during startup or when there's breakup of the scum blanket, sudden temperature changes, or overfeeding. In this case, increasing mixing, reducing or stopping feeding, and stabilizing the temperature can help control the foam. Low methane production is another challenge. often indicated when CO2 levels rise above 40%. This might happen during startup or if temperature control is uneven. Stabilizing the temperature and controlling both feeding and withdrawal rates are crucial to improving methane output. Lastly, high solids in the supernatant, with TSS over 1000 mg/L, can occur if you're drawing from the wrong level. It's important to draw from the correct level, as supernatant can be very high in solids even after several days of settling. Proper level management helps ensure clear, stable effluent. Understanding these indicators and their causes allows us to respond quickly and keep the anaerobic digestion process healthy and efficient. Aerobic sludge digestion is quite different from anaerobic digestion, and it's actually more of an extension of the secondary treatment processes. In this method, we supply air and mixing to the solids held in a tank, but there's no artificial heating involved. One key point here is that no external food source is added to the organisms in the tank. Instead, they feed on the existing sludge, which leads to a process called endogenous respiration. Essentially, the organisms start eating each other, breaking down the sludge further and releasing carbon dioxide and water vapor as byproducts. When we look at efficiency, aerobic digestion typically reduces volatile solids by about 20 to 40%. This usually happens over a solids detention time of around 20 to 30 days. While it's effective, it's generally less efficient than anaerobic digestion, which can achieve higher reductions in a shorter time. Now, one of the benefits of aerobic digestion is its impact on pathogens. Because of the predation by a variety of organisms during the process, the level of pathogens in the sludge is significantly lowered. This makes the final product safer for disposal or reuse. Finally, let's talk about simplicity. Aerobic digesters are quite straightforward, which makes them attractive for small to medium-sized treatment plants. They are often used in package plant configurations because of their ease of operation and maintenance. Overall, while aerobic digestion might not be as fast or as high yield as anaerobic processes, its simplicity and pathogen reduction benefits make it a valuable option in many wastewater treatment scenarios. Let's talk about operating aerobic digesters. They're actually quite simple to run, which makes them a great choice for smaller facilities. However, even with their simplicity, proper operation is still crucial to ensure they work effectively. First, maintaining dissolved oxygen levels is key. You want to keep it around 1 milligrams per liter. If it drops below that, the sludge can produce a foul, rotten melon odor, which gets worse the longer it goes on. To avoid serious odor issues, at least 0.5 milligrams per liter should be maintained at all times. Next, controlling feed and removal rates is important. The amount of sludge you add depends on how much solids need to be removed from the secondary treatment process. Similarly, the rate at which you remove sludge depends on the digester's current level and your available dewatering and drying capacity. Regular cleaning is also essential. Every 3 years, you should take the digester offline to clean it thoroughly. This helps restore tank volume by removing sediment and allows you to inspect submerged equipment to prevent issues down the line. Now let's focus on weekly monitoring tests, which are critical for maintaining optimal operation. Checking the pH is vital. Ideally, it should stay above 7. If it drops below, that could indicate problems like unwanted nitrification, which causes acidic conditions. You should also measure total solids, or TS, in the feed sludge, the digested sludge, and the withdrawn sludge. Typically, TS ranges from 1.5 to 4%. Volatile solids reduction is another key indicator. It tells you how effective your digestion process is. Keep in mind, over time, the V's reduction may decrease because sediment can reduce the digester's volume, so tracking this helps you gauge performance. Finally, always measure dissolved oxygen with a calibrated dew meter. Ensuring adequate aeration is critical for the digestion process to proceed smoothly and efficiently. By paying attention to these points, you can keep your aerobic digester running effectively and ensure it continues to perform well as part of your overall wastewater treatment process. Let's take a closer look at sludge thickening and dewatering. Even when sludge is considered thick, say around 5 to 6% total solids, it still contains over 90% water. Storing and transporting all that water alongside the solids isn't practical, which is why we use various methods to separate the solids from the water effectively. One common method is gravity thickening. This technique uses gravity itself to let the solids settle at the bottom of a tank, compacted by the weight of the overlying sludge. Typically, this process can bring the solids concentration up to around 2 to 4%, and sometimes up to 6% if polymers are used. Another method is dissolved air flotation. Here, tiny air bubbles attach to the sludge particles and float them to the surface, forming a layer that can be skimmed off. This process works especially well for secondary sludges. Then we have belt filter presses. Think of two endless belts moving over rollers. These belts press the sludge between them, squeezing out the water. For this process to be most effective, polymer conditioning is essential. Depending on the sludge type, this method can achieve solids content between 17 and 35%. Centrifuges are another option. They spin the sludge at high speeds in a rotating bowl, using centrifugal force to push the solids outward to the wall of the bowl, where they are compacted. Centrifuges can typically reach solids contents of 5 to 30%, with recovery rates between 90 and 99%. Lastly, in smaller or warm climate areas, sludge drying beds are quite common. These are shallow basins where sludge dries through evaporation and percolation. While they can achieve over 95% solids, a more typical range is around 70 to 80%. It's also important to note that chemicals called polymers can enhance many of these dewatering and drying processes. They improve performance and can significantly reduce processing time. Connecting all these methods to the overall goal, reducing water content, helps us manage sludge more efficiently and cost-effectively. Gravity thickeners use the force of gravity to help separate solids from water in wastewater sludge. The key idea here is that heavier solids will settle to the bottom under their own weight, leading to compaction. This process relies on gravity, so the design of these thickeners is usually circular or square, and they look quite similar to secondary clarifiers. Inside, you'll find several important components. There's a feed line and baffle that help distribute the flow evenly, ensuring the sludge enters smoothly. Then, there's a sludge rake mechanism that moves the settled sludge toward the bottom center of the tank for removal. You'll also see vertical steel pickets mounted on the rake, which help in the movement and settling process. An overflow weir allows the clarified water to exit, while a scum box or tilting weir handles floating scum and solids. Finally, there's a sludge withdrawal line for removing the thickened sludge. When we talk about performance factors, several are particularly important. The type of sludge matters. Primary sludge thickens best without becoming septic, but secondary sludge can be more challenging due to lower solids content and denitrification issues. The age of the feed sludge also impacts performance. Older sludge is more prone to gasification caused by denitrification and septic conditions, which can cause particles to float instead of settle. Temperature plays a role too. Warmer sludge tends to gasify more because biological activity increases, making settling less effective. Sludge blanket depth is another critical factor. It's all about balancing. You want a thick enough blanket for proper compaction without letting solids reach a point where they gasify or cause issues. Finally, hydraulic and solids loading need to be properly designed to match the actual flow and solids coming into the unit. If the load is too high, the thickener won't perform efficiently. Typically, the solids content without polymer addition is around 2–4%, but with polymer addition, you can push that up to about 6%, maximizing solids removal. So, understanding these factors helps us optimize the gravity thickening process, which is a vital step in wastewater treatment to improve sludge handling and reduce downstream processing challenges. Now let's talk about dissolved air flotation, or DAF, thickeners. This process works similarly to what happens during sludge denitrification. Essentially, tiny air bubbles attach themselves to sludge particles, causing them to float to the surface. Once there, they form a sludge layer that can be easily removed. How does this process actually work? Well, the sludge layer is skimmed off into a hopper, creating a thicker, more concentrated sludge. A significant part of the separated water is recycled back into the feed sludge line after being saturated with air. This provides the bubbles needed for flotation. The treated effluent then exits the far end of the unit and is sent back into the overall treatment plant flow. To improve separation and thickening, polymers are often added to the feed sludge. Now, let's highlight some critical performance factors. First, the type of sludge matters. Secondary sludge tends to perform better than primary, and younger sludge thickens more effectively than older sludge. The air-to-solids ratio is vital. It's essentially about how much air is available to float the sludge particles. This depends on the air pressure in the saturation tank, which controls how much air gets into the recycle stream. Recycle rate is also important. Higher flow rates carry more saturated air to the sludge inlet, enhancing flotation. Another key aspect is the thickness of the floating sludge blanket, which is typically kept between 6 and 8 inches deep. The scraper speed influences this thickness, but it's important to set it correctly to avoid solids carryover. Finally, let's look at some performance guidelines. Without polymers, the solids loading is usually between 0.4 to 1 pounds per hour per square foot, and with polymers, it can go up to 2. Hydraulic loading rates are generally around 0.5 to 1.5 gallons per minute per square foot, increasing slightly with polymers. Recycle rates are typically between 100 and 200%, and the air-to-solids ratio should stay within 0.01 to 0.1. The goal is to produce a thickened sludge with solids content of around 2 to 4% without polymers, or 3 to 5% with them. Overall, when DAF units are operating properly, they should produce an effluent containing less than 100 milligrams per liter of total suspended solids. That's the key to ensuring the process effectively clarifies the water and supports the overall treatment system. Now, let's take a closer look at belt filter presses, which are an essential part of the dewatering process. These presses use 2 endless belts that run over a series of rollers mounted on a galvanized steel frame. The process begins with conditioning the sludge, often with polymers, to prepare it for dewatering. Once conditioned, the sludge is placed in a drainage area where it starts to lose water before being fed between the 2 belts. As the sludge moves between these belts, it is pressed between perforated and non-perforated rollers. This pressing action forces water out of the sludge, which then travels out of the belts and is collected for return to the treatment plant. The remaining sludge, now in the form of a cake, is scraped off the belts and conveyed away. Meanwhile, the belts are washed to prevent clogging and ensure continuous operation. An important aspect of this system is sludge conditioning. Proper conditioning, especially with cationic polymers, is critical for effective dewatering. The polymer dosage needs to be carefully optimized, and maintaining a consistent sludge feed is essential for reliable results. Next, let's consider belt tension pressure. Adjusting the tension roller setting controls the pressure applied to the sludge. If the tension is too tight or too loose, it can affect dewatering efficiency. Finding the right tension is a matter of experience, and the goal is to set it just right for optimal pressure without damaging the belts. Belt speed is another key factor. The belts must move fast enough to spread the sludge over a sufficient area for drainage, but not so fast that water is carried along with the belts, leading to washout and poor effluent quality. Ideally, you want the slowest speed possible while still ensuring effective drainage. Finally, the choice of belt type plays a role. Different materials like nylon or polypropylene have varying porosity levels. Higher porosity belts drain water faster but tend to produce lower quality effluent. Conversely, low porosity belts may cause binding or plugging, leading to frequent washouts. Selecting the appropriate belt depends on the specific sludge characteristics, whether primary, secondary, or digested sludge, and their respective polymer requirements, cake solids, and hydraulic loads. Understanding these factors helps us optimize the belt filter press operation for better dewatering and overall treatment performance. Let's take a closer look at sludge drying beds. These are typically used in smaller to medium-sized treatment plants, usually less than 5 million gallons per day. The reason for this is that they require quite a bit of land and manpower to operate effectively. Now, moving on to sand drying beds. These consist of shallow-lined basins, which can be made of concrete or earthen material. Underneath, there's perforated pipe installed beneath a layer of gravel about 12 to 18 inches thick, topped with 8 to 12 inches of sand. Sludge is poured onto the bed to a depth of around 12 inches. As the water in the sludge evaporates and percolates down through the sand, the sludge gradually dries out. When it has cracked all the way down to the sand layer, we can remove it using a shovel, wheelbarrow, or a small skid loader. These beds can dry sludge to over 95% total solids, but typically, we see about 70 to 80%. Let's compare that to asphalt drying beds. These are quite similar to sand beds, but feature a hard asphalt or concrete surface instead of sand and gravel. This hard surface allows us to use sludge mixing equipment, which speeds up the drying process. Additionally, because we can mix the sludge, we can pour it at a greater depth, between 18 to 30 inches, and still achieve rapid drying. These beds are particularly effective when preparing sludge for composting, as they facilitate quicker dewatering. Lastly, there's the vacuum filter bed. This setup involves a shallow concrete basin with an under-drain system, which is covered with porous materials like pumice bricks or perforated panels made of stainless steel or plastic. The key here is the vacuum pump, which creates a suction underneath the panels. When polymer-conditioned sludge is poured onto the bed, the vacuum rapidly draws water out of it. This process can reduce the total solids from the sludge to about 15 to 30% in just hours or a few days. Once the dewatering is complete, we clean out the bed using a skid loader or a small backhoe. All of these methods connect to our overall theme of efficient sludge management, helping us reduce volume and prepare the sludge for further treatment or disposal. Each has its advantages depending on the plant size, space availability, and processing goals. Now let's talk about biosolids, which are essentially treated sewage sludge that we use beneficially or dispose of safely. Since sludge contains nutrients, organic molecules, and trace metals that plants need for growth, it actually makes an excellent soil conditioner. When we treat sludge properly for this purpose, we call it biosolids. One of the main benefits of biosolids is that, when applied correctly, they can significantly improve soil conditions. They help the soil retain water better and enhance aeration, which promotes healthier plant growth. However, there are 3 major concerns we need to keep in mind. First is pathogenic contamination, which we usually measure using an indicator organism called fecal coliform. Then, there's vector attraction reduction, or VAR, which is about preventing animals from being attracted to the sludge. And finally, we must be cautious about toxins, like heavy metals, PCBs, and nitrogen compounds, which could potentially contaminate the environment. Now, regarding regulations, the main law governing the disposal and use of wastewater sludge is Title 40 of the Code of Federal Regulations, Part 503, often just called the 503 Sludge Regulations. These rules specify the treatment techniques needed to reduce pathogen levels before applying sludge to land. There are 2 classes of biosolids. Class A, sludge, is of high quality. It's safe enough that it can usually be sold or given away, provided it also meets VAR and heavy metals standards. Class B, sludge, is of lesser quality, but can still be land applied if proper management practices are followed, and it meets the same safety requirements. Finally, it's important to remember that operators have key responsibilities. They must carefully follow all relevant regulations and ensure the product is as safe as possible. Proper use is critical because failing to comply can lead to serious legal consequences, including civil or even criminal prosecution. Ultimately, our goal is to protect public health and the environment while making effective use of biosolids. Let's talk about composting and disposal options for sludge. Starting with composting, specifically Class A composting, It's a thermal aerobic biological process. Essentially, sludge is placed in windrows along with wood chips or mulched green waste. Bacteria then break down the material, generating significant heat in the process. To meet Class A standards, we need to maintain temperatures above 55 degrees C or 131 degrees F for at least 15 days, turning the piles 5 times during that period. Keep in mind, operating a compost facility like this requires a special compost facility operator license. Next, surface disposal involves applying sludge directly to the land surface, but it's important to do this well above the crop's agronomic uptake rate. This can be done by injecting the liquid sludge 1 to 3 feet below the surface or spreading solid sludge and plowing it in. Of course, this requires a permit from the New Mexico Environment Department Groundwater Quality Bureau, and groundwater monitoring is essential. When done properly, surface disposal can be a safe and cost-effective option. Then there's landfilling, which is generally considered the least desirable option. It wastes valuable landfill space that could otherwise be used for beneficial reuse of the material. Landfilling should only be used when economic factors or poor sludge quality make other options impractical. This method requires a detailed sludge disposal plan and a licensed special wastes hauler. Throughout this process, it's important to remember that dealing with sludge often involves obtaining permits or approvals from federal agencies like the Environmental Protection Agency, as well as your state's Environment Department. Proper solids handling, through careful process control, regular monitoring, and strict adherence to regulations, is key to running wastewater treatment facilities safely, economically, and responsibly. By doing so, we can ensure that sludge is stabilized, dewatered, and either reused beneficially or disposed of safely, protecting both public health and the environment.